uh, I made a list of formulae, whatever. Okay, it's advisable to actually write down all of these before solving the question, because now we will be moving on to boundary value problems, and sometimes things can get little hard in that, little complicated. So it's useful to have this formula in front of you. If they are in front of you, it will help to strike. Like suppose you see this formula, then the logic may strike that yeah, I can use this. So that way it might be helpful. So yeah, this is an entire list, and this covers all the formulae that we have done till now in this chapter, and I guess it covers all the formulae we have done so far in the entire course also. Right. So we will move on to solving a problem on boundary value conditions. Boundary value conditions are just these, right? And this condition, which I have already derived before. So what's more important is how to apply them. So we will see that now. Okay. I'm going to solve problem 4.22 of Griffith. I'll read the question. A very long cylinder of dielectric material is placed in an otherwise uniform electric field E0. Find the resulting field within the cylinder. Okay? So your situation is you have a region with a uniform electric field E0. Okay? Now in this region you place a cylinder, very long cylinder, so extending to infinity, made of dielectric material. Your aim is now to calculate the field inside the cylinder. Note that it's given it's a linear dielectric. Note that like in capacitor 11-12 we just had two capacitors, you put a dielectric, the field here is E0 by K. That will not solve the question here, mainly because it will not just be by K. The reason being, once you put this dielectric cylinder here, there will be charges induced on the surface. So there will be a sigma B. Correct. Now this sigma B will also exert an electric field. So at some random point outside here, the electric field will be superimposition of E0 and sigma electric field due to sigma B. That divided by K, that net field divided by K will be the answer. That is correct. But to calculate the net field due to the sigma B, it's going to be challenging, right? So what do we know right now? We know that this is a linear dielectric. So what can we write for a linear dielectric? P is equal to epsilon naught xc into vector E. Note that this vector E is the same E as in Gauss law, so it is net electric field at any given point. Okay. Now consider any location inside the cylinder here, right? We know that del dot D is equal to rho free, and we know rho free is equal to 0. Also we had derived rho bound is minus xc by xc plus 1 into rho free. Now since rho free is 0, rho bound is 0, is equal to 0. Rho bound is 0, so we know rho bound is minus del dot P, which is 0, which means everywhere inside this dielectric P has no divergence. So all over this dielectric the vector P is constant. So inside the dielectric P is constant. Note, I am not saying P is radial, I mean P is constant. So if I take the top view, this is the cross section, this will be your electric, this will be your polarization, vector P. It is not radial like this, it is not radial, it is constant, the vector is constant. Now since P is constant and it's proportional to E, E is also constant. Right? Okay. So what do we know now is that E at all points is the same. Now, there has to be some induced charge, right? Because it's a dielectric material, there has to be some sort of induced charge happening. Otherwise, there can be no polarization. Now we know that there is no volume charge, so there must be some surface charge. Let us try that. Sigma B is P dot n cap. So if I consider this cross section, this is my cross section top view, and this is the direction of P, right? So at any point, let us say I consider this point at an angle theta from, this is the line corresponding to the electric field external, E naught initial. So this will be n cap and this will be vector P, this angle being theta. So P dot n cap is just P cos theta, right? So the bound charge which comes on the surface will vary radially with theta. Note that it does not change along this because this is infinite and it's constant like this, but it varies along this circle. So it varies with theta. So now our aim is that since we know electric field everywhere is constant inside, and the question asks us find the electric field within the cylinder, if we can find it at any one point, we know that it is the same everywhere. So for that purpose we will choose a good point, like a symmetric point which will make our calculation easier. That is any point on the axis. Consider this point. Right? Our aim is to find the electric field over there. So we can say electric field will be a superimposition of external plus the one due to bound charges. So there are two methods now. You take any small ring over here, okay, of small thickness, and using that you find the electric field here. It will only be like this. It will only be along this direction. You find that electric field and integrate from minus infinity to plus infinity, right? From minus infinity to plus infinity you can integrate. Another method is applying boundary conditions. So because this method of using discs we have done quite often in 11th 12th, काफी बार किया है हमने इंटीग्रेशन. मैं बाउंड्री कंडीशन से सॉल्व करना चाहूँगा इसको, राइट? बाउंड्री कंडीशंस क्या कहती है इलेक्ट्रिक फील्ड की? E perpendicular on the outside minus E perpendicular on the inside is equal to sigma by epsilon naught. Okay. So E perpendicular on the outside. Okay. This can be now because there will be a sigma B here. We know that on the inside by Gauss law this कट कर देना इसे. Perpendicular on the out is equal to E naught cos theta plus okay. This boundary condition we know. Now we also know that by principle of superposition we want this component. If this is your cross section, then the net electric field outside will be this vector E naught plus the electric field due to this sigma B, right? So we want that the component of this net field along n cap, along this n cap. So we can just write this thing to be, this angle is theta. So E naught cos theta plus this is sigma b here, and the electric field it will exert on the outside will be just sigma b by 2 epsilon naught along n cap, right? And E perpendicular, let us say now E perpendicular on the inside is equal to E cos theta, where I am saying that inside the net field is E along this direction, same direction as E naught. I am assuming let this is the net field, ठीक है? तो इसको फिर ऐसे प्रोजेक्ट किया along n cap, so E cos theta आ गया. अब इन दोनों को इक्वेशन में डाला. We have these two equations now. Fit it here. Okay. Now we have a boundary equation for this D. Sigma free. Which we know because it's a linear dielectric reduces to E out. Plus is nothing but out. E perpendicular out minus E in, E perpendicular in equal to 0, because there is no free charge. In the given question we don't have any free charge. So on this boundary we will not have free charge. So sigma free will be 0 and sigma b will be whatever we have calculated through P dot n, P cos theta. Now E out is 1, it's just E naught, sorry. E naught into E out. So E naught cos theta epsilon naught plus sigma b by 2 epsilon naught is equal to epsilon in, which is E, right? Yeah, epsilon naught into 1 plus x. We have they have not given us that, so we use this same thing. Into E in, which is E cos theta. Now put the value of sigma b as P cos theta. Cancel this epsilon naught. It is easy enough. So we get E naught cos theta plus P cos theta by 2 epsilon naught equal to 1 plus xc to E cos theta. P is again epsilon naught xe, where E is the electric field net inside, right? So we can write it as plus epsilon naught c into E. Note that I am using this E, which is same as this, because in the equation vector P equal to epsilon naught xc vector E. This E is the net electric field, and we have said let the net electric field be this capital E. So I am using the same. Note that because that's important. Now solve for E. This is pretty straightforward. Is equal to E into 1 plus xc minus xe by 2 into E into 1 minus xe by 2. So electric field E is equal to 2 E naught by 1 minus xc by 2. Oh, sorry, 1 plus. Sorry. Yeah. Is that correct? 2 plus xc, I think. Yeah. So that's your answer. Again, as I said in the beginning also, we generally used to do like for a capacitor, the field is E naught, and inside a dielectric it's E naught by K. So it's not the same thing here, because K, the dielectric constant, is 1 plus Xe. This answer is not E naught by 1 plus XC. Why? Because the sigma which is induced here changes the electric field outside. E naught is the electric field before you had put this, before you had put the dielectric. That is not the same as the external field with the dielectric. If you calculate external field with the dielectric and then you divide that by 1 plus Xe, you will get this answer. That part is correct. But the problem is calculating that net external field itself will be so problematic because the sigma b varies as cos theta. That itself will be troublesome, so we would rather adopt to this approach. Note the thinking here, the way of approaching the question. First, we did not know anything, we just had this E naught situation and you are given this dielectric. Now when you are given a dielectric, it's a linear dielectric. So moment you see linear, you should write the equations for linear dielectric. P equal to epsilon naught Xe E, then rho bound is equal to minus Xe by Xe plus 1 into rho F, rho free that is. So that equation relating rho bound and rho free gave you what? Rho free is 0, so rho bound is 0. There is no bound charge anywhere. So if there is no bound charge anywhere, we know rho b is minus del dot p. So we see that del dot p is 0 everywhere, which means polarization is uniform everywhere. Once polarization is uniform everywhere, electric field must be uniform everywhere. So because electric field is uniform everywhere, we got the idea that if we calculate it at any one good symmetric point, we got the value everywhere. So we don't need to worry more. Now calculating at a symmetric point, to do that you use your equations, whichever you are given. First thing now since you have to calculate at the symmetric point, first you need the charge distribution. So there is no volume charge, there has to be some surface charge, otherwise there is no sense of polarization. So find the surface charge. Now once you found the surface charge, the electric principle of superposition gives you that electric field is electric field due to external plus electric field due to this sigma bond. Vector summation will give you your electric field. Alternately, what you can just think of is apply the boundary condition. Once we basically want E here, correct? And you know that it's the same everywhere. And E outside is easily calculable by superposition. E outside is nothing but E naught plus the electric field due to this sigma b. Sigma b very close to the surface, the electric field just be sigma b by 2 epsilon naught. So you know the electric field outside and you have to find the thing inside. So the immediate thing that should come to your mind is boundary condition. So we applied the appropriate boundary condition. We could have applied for electric field, but then we would have to also consider sigma bound in the equation. When you have an easier choice where sigma free is 0, then go for that. Okay. Now once this struck, the rest was pretty straightforward. Just keep replacing variables. Like over here d was replaced by epsilon e. Sigma b we replaced with p cos theta. P we replaced with epsilon naught x e. And you just move on. Right? This is why I said कि initially सारी equation लिख लो, because एक बार equation सामने है तो देखना आसान हो गया कि ठीक है पहले हमने निकाल लिया रो 0 है, फिर ब्लाइंडली स्ट्राइक नहीं करता कि डेल डॉट पी भी 0 होगा, लेकिन अगर सामने इक्वेशन है तो दिख जाएगा कि हाँ रो 0 है, रो बाउंड 0 है तो डेल डॉट पी 0 है, मतलब पी यूनिफॉर्म है, पी यूनिफॉर्म है तो फिर पी इक्वल टू एप्सिलॉन नॉट एक्स ही है तो ई भी यूनिफॉर्म होगा. ऐसे अगर इक्वेशन सामने हो तो स्ट्राइक करने लगेगा तुम्हें. Right? Okay, for practice on this, because I feel this questions on boundary value problems are going to be the harder questions that come from this chapter. So there are 3 or 4 questions which are given on page 190 of 3rd edition of Griffith. I suggest you solve all of them. This was the first question of them, and I suggest you solve the rest also, so that you are able to think. तो वो जो thinking आनी चाहिए systematic प्रोसेस कि पहले ये स्ट्राइक किया फिर वो स्ट्राइक किया फिर ये सिस्टमैटिक प्रोसेस बिल्डअप होगा प्रैक्टिस से तुम्हारा. सो आई सजेस्ट कि तुम ये सॉल्व करो.